Swayam Prabha. Digital India. Educated India.
Welcome to this class. In last few classes we have discussed about particle in a box problem. We looked at the solution of particle in a one dimensional box problem. We also looked at the free particle problem. In today's class we will go beyond one dimensional box and we will go actually to higher dimension. In that case we are going to study particle in a three dimensional box. So, when we say particle in a three dimensional box, we can imagine a cuboid let us define the three axes. Let us call this x, y, c, and the sides are a along x axis, b along y axis, and c along z axis. Let us consider this cuboid a box with the dimension a, b, c, where the particle is. Like we had the particle in a one dimensional box, we defined that the particle experiences zero potential energy within the box, one dimensional box, and infinite potential energy outside the box. We also would use the same definition over here. So, here we would say that the potential energy is 0 for x between 0 and a, y between 0 and b, and z between 0 and c. So, this is the origin 0, 0, 0. So, this is the potential energy within the box, and outside the box the potential energy is 0. So, like in the elsewhere. What about the kinetic energy operator? The kinetic energy operator we have already seen, a square by 2 m if you see, the kinetic energy operator is now expressed in terms of the second derivative with respect to x, y, and z. Now, the Hamiltonian is of course sum of kinetic energy and potential energy operator, and when we solve this problem we would write down the final Schrodinger equation H I equals E psi. If you remember the solution of particle in a one dimensional box, you would remember that the wave function psi was a function of x alone, because the particle was restricted to move only along x axis or along x direction. But here, since the particle can go around all three dimensions in this cuboid, so therefore, the wave function psi will have a functional dependence on x, y, and z. In this case, this will be the final wave function that we are looking for. We are going to express this final wave function in terms of three functions, f of x, g of y, h of z. What we have done here is that we have used the so called separation of variable technique. We see that our potential energy operator is 0 throughout. The kinetic energy operator has terms which have only x dependence, only y dependence, and only z dependence. There are no terms in our Hamiltonian operator which have xy or yz or xz dependent. So, since there are no cross terms, we can assume that this way of writing the wave function, that the wave function can be expressed in terms of three functions, one which will consider the x direction alone, the other which will take care of the y dimension, the third one will take care of the z direction. So, this separation of variable, this approximation we are assuming, and then we would show that by making this assumption we do not run into any trouble, we perfectly satisfy all the boundary conditions of this problem that are required to be satisfied. When I look at this wave function that I have defined as f of x, g of y and h of z, I see that this wave function will eventually be acted upon by this kinetic energy or potential energy operator. So, the kinetic energy operator has some second derivative term. Let us first see what happens when I use this second partial derivative on this function psi. So, since the partial derivative is with respect to the x coordinate alone, so therefore, the g of y and h of z will remain unchanged and the operator will act only on the f function. So, therefore, I can write or in shorthand I can write this expression as f double prime, which represent the second derivative with respect to f, g and h. Similarly, I can write down the second derivative with respect to y as f, which is a function of x, second derivative of g, which is a function of y, and h, which is a function of z. Because when I am taking second derivative of with respect to y, the x and z function will remain unchanged. Similarly, when I write d square by d z square and apply on psi, I get f g h double prime. Okay. So, we will use these forms that we have discussed so far into our Hamiltonian. So, this is the starting point. We have h psi equals E psi. So, therefore, minus s square by 2 m d square these are the partial derivative with respect to psi, which is f g h equals E f g h. So, this is my wave function. So, I am dropping the functional dependence of f, g and h. Please remember, f has only x dependence, g has only y dependence and h has only z dependence. When I do the second derivative on this function, the results I have already written down, so that we can continue our discussion further. In the right hand side. So, the first term is coming when I am differentiating with respect to x. So, the second term is coming when I am differentiating with respect to y. The third term is coming when I am differentiating the function with respect to z. And in both right hand side and left hand side, I can divide f g h. In that case, I will be left with and this E is the energy in the Schrodinger equation, and this is of course going to be a constant. I can rewrite this equation in the following way. I am going to take the g and h functions to the right hand side. If you look at this equation, the left hand side depends only on x variable. The right hand side, of course, this is a constant, has some functions which depend on y, some functions which depend on z. So, in the left hand side I have got functions which depend on x, the right hand side I have got functions which do not depend on x, but depend on y and z. So, when I have such a situation, when the left hand side depends on some variable and the right hand side depends on other variables, in that case I can see the left hand side and also the right hand side are actually independent of any of these variables. So, therefore, the left hand side I can say this is a constant. So, and I define this constant as E of x. So, we will continue our discussion with the left hand side, but before that I can also do the same exercise by keeping the g function on the left hand side, which will be a function of y, and f and h on the right hand side, which will be the function of x and z, and argue that since left hand side depends only on y, whereas the right hand side does not depend on y, but since left hand side and right hand side are equal, so therefore the left hand side function must be a constant, and therefore this term h square by 2 m z double prime by g would also be a constant. I would perhaps call that E y, and similarly I would call minus h square by 2 m h double prime by h as another constant. I would call that by E z. So, let us come back. So, this is what we have. Is a constant. All right. So, now let us look at these terms individually. So, I will just do for the first term, and the rest the second and third will simply follow the same procedure. So, when I rewrite this equation, if you look carefully, we have already seen a term an equation like this: minus a square by 2 m d square by dx square, and a function, second derivative of a function, and in the right hand side we have E x of m. So, you would identify immediately that this is a Schrodinger equation with respect to x axis, with respect to x dimension for a function f, and we know its solution. We can also write down the homogeneous second order differential equation. And its solution is also something that we already know. If you remember, so this 3-dimensional box problem has become 3 independent 1-dimensional problems, and we are currently dealing with one of these 3 one-dimensional problems. So, in this case, the wave function can be written down as a linear combination of 2 exponential functions, and once we have this linear combination of 2 exponential functions, then we can put boundary conditions, and here, like the particle in a 1-dimensional function, we have to have the same boundary condition that at the interface in the x along x axis, the wave function must be continuous. So, when I am talking about x axis, I should say that the wave function should be continuous at x equals 0 and at x equals a, because that is the length of the box along x axis. So, when I impose this condition, we would actually get back the solution that we already are familiar with as a particle in 1-dimensional box. In that case, what I would get is that the function f, which will be a function of x, will be 2 by a under square root sine n1 pi x by a. Please compare this function with respect to the one dimensional particle in a one dimensional box problem. So, we had in that case in this press, instead of a, that was capital L, which was the length of the box, the same here, and here we have this n1, the quantum number n1, which can be like the previous case, go from 1, 2, 3 and so on. So, therefore, this function f has a dependence on one quantum number n1, and similarly I can write the function g, which will be a function of y as n2, and in this case I have and the function h, which will depend on z as 2 square root 2 over c sin n3 pi z divided by c, where a, b and c are the size of the cuboid along x axis, y axis and z axis, and in this case n2 is also goes 1, 2, 3 and so on. N3 can also become 1, 2, 3. What about the energy? We see that the energy corresponding to the Schrodinger equation for f function is E of x. So, E of E x will have a dependent will be written down as this one. E y and E z where n1, n2 and n3 are the quantum numbers we have here. The sum of the three, Ex plus Ey plus Ez, would be the total energy of the system, which is given as mc square. This is the total energy. Now, this energy, total energy, depends on three quantum numbers n1, n2 and n3. To make some more interesting outcomes of this problem, we will make one assumption, is that instead of dealing with a cuboid, we will make this problem as a cube. So, when you have a cube, the only difference is that A, B and C become equal. So, therefore, the energy for a particle in a three dimensional box with size with all sides equal is simply would become and the wave function, the final wave function psi would be the product of f, g and x, f, g and h, which will simply be this wave function. Please notice that the energy function has h square by 8 ma square. So, a is the side of the cube, and we have three different quantum numbers n1, n2, n3, and the wave function also has dependence on n1, n2, n3 quantum number, where these three functions are product of the final wave function is product of three wave functions, whereas the final energy is the sum of three energies. So, this is a typical outcome when one uses this separation of variable, where the final wave function, when you impose separation of variable, the final wave function becomes the product of wave functions in the individual dimensions, and the final eigenvalue becomes the sum of the eigenvalues in the individual dimensions. This is a general rule that you would actually encounter also in future. We will use this expression and learn something about the energy levels of particle in a 3-dimensional box next. So, if you just to keep refresh your memory. So, our total energy E had where n1, n2, n3 are 3 independent variables. Each n1 and each of n1, n2 and n3 would go from 1, 2, 3 and so on, so on. So, the lowest possible values of n1, n2 and n3 are all 1. So, let us say this is n1, this is n2 and this is n3 and this is my total energy E. If n1 is 1, n2 is 1, n3 is 1, what would be the energy? The energy would be 1 square plus 1 square plus 1 square. So, therefore, 3 h square by 8 m a square. This is the lowest possible energy in a particle in a 3-dimensional box. If you remember, the lowest possible energy in the particle in 1-dimensional box was a square by 8 m l square. There was no 3 in it. So, this energy is the 0 point energy for now. What are the next possible values of n1, n2, n3? They can become 2, but then before we make all of them 2, we can see that I can write like this 1 1 2. What would be the energy of this state? That would be 1 square plus 1 square plus 2 square. So, 4 plus 2 6. So, therefore, I will be 6 h square by 8 m a square. I can also do as 1 2 1 and you will see the energy of this state is also same as 6 h square divided by 8 m a square. There is one more function 2 1 1 which also have the same energy. So, now what we see is that we will have 3 different state functions with 3 different state functions represented by 3 distinct eigenfunctions which will have same eigenvalues. This is a case of degeneracy. So, we see that this energy level is threefold degenerate. If we plot energy axis, this will be the energy of 1 1 1. So, here n1 is 1, n2 is 1, n3 is 1. This energy is 3 h square by 8 m a square and this is one fold degenerate. That means, there exists one eigenfunction which has this eigenvalue. The next set of eigenfunctions 1 1 2, 1 2 1 or 2 1 1, all 3 of them have same energy. So, I write it like this. So, this represents 1 1 2, this represents 1 2 1 and this represents 2 1 1. We can write 3 different state functions or 3 different eigenfunctions for each of these 3 levels, whereas their energies are all same, that is 6 h square by 8 m a square. So, these energy levels form a threefold degenerate system, threefold degenerate energy level. So, in this degeneracy, the degree of degeneracy, this is so for the lowest eigenvalue, the degree of degeneracy is 1. For the next eigenvalues, the degree of degeneracy is 3, because there exist 3 linearly independent eigenfunctions that have same energy. We can continue our discussion further by making 2 labels n2 and n3 as 2, whereas n1 is 1, or similarly we can do it 2 2 1 2 or 2 2 1. You would see these 3 labels also would represent a 3-fold degeneracy. So again, why they are 3-fold degenerate? Because there exist 3 different eigenfunctions that would have same eigenvalues. The next eigenvalue would be 2 2 2, and you can always find out this will be 2 square plus 2 square plus 2 square. So, 12 into a square by 8 m a square, and this will be again 1-fold a non-degenerate solution. This degeneracy that we encountered in this problem is because of the symmetry of the problem. If you see that if I write this eigenfunction corresponding to 1 1 2 1 2 1 2 1 1, they would all be more or less similar except for the fact where x, y and z are there. So, if I make an interchange between x axis, y axis and z axis, you would see I can reproduce the same wave functions. So, therefore, the 3-fold degeneracy that I am seeing, that is because when if I rotate my Cartesian axis from x to y, y to z and z to x, in that case I actually reproduce the same another wave function. So, the symmetry that we have in our problem is the root cause of observing this degeneracy. If we had a particle in a cuboid where A is not equal to B is not equal to C, in that cases there is no such symmetry. So, therefore, we would not see this degeneracy. But mind you, in several higher dimensional cases you may also see degeneracies even when there exists no symmetry, and in those cases we call them accidental degeneracy. These degeneracies are not driven by the symmetry of the system, but they are there because of the accidentally the numerical values of the eigenvalues become equal, and therefore they are degenerate. That is all for today's class. Thank you very much.